Hello everyone, this is Wenning Liu from Glendale office. Today, I'm going to give a brief introduction on two new features of NL step for solution 400. The first one is the smart convergence control for solution 400. So in general, as you know, the NL step in solution 400 provides comprehensive control parameters for solution convergence. So as you can see from the table, there are totally 8 keywords and 14 cards. So in general, this is very helpful and useful for advanced users of Nastran tools. But sometimes for application engineer and also for the beginner users of Nastran, maybe so many inches are too complicated for them. So therefore, we just try to provide a smart and small control for the convergence of nonlinear analysis. With the new keyword CTRLDEF, so what the user can do is just select the value for this keyword and also decided if they will use a fixed time step or adaptive time step. So they can use the Q-linear, mildly, severely, or even blank. So how to determine the value for CTRLDEF? Here are some examples. So first we can see, so this is Q-linear. In general, if the model only involves the nonlinearity from the contact and the geometry and the materials are material is characterized by the nonlinearity. Also, maybe involve some of the contact nonlinearity. So you can use mildly for CTRLDEF. If you just strain material nonlinearity and also contact nonlinearity, so we can recommend to use severely. Of course, such example and are only some suggestion or recommendation. It's not a strict limit or requirement because you see the model and problem maybe gets much more nonlinear. So due to the boundary condition, also maybe the combination of some nonlinearities. So if you would like to get the default setup for smart control, you can refer to the new release of the QRG file. So you will get a detailed setup for time increment and convergence tolerance. Here is the example. So this is a two-side contact involving the large displacement, large strain, and also large sliding problem. So for the NL step card, you can see we only select CTRLDEF as severely and then decided to use adaptive time stepping. Here is the result. So let's come. So my movie display has some problems. I have to back to the PPT file format. Can you see the movie?
No.
No, not yet.
No?
No.
Sorry. So let's go ahead.
Oh, yeah. See it.
Can you see?
Yeah. But no moving.
No movie?
Not yet. That's fine. We can share the movie later, right?
Okay. So now let's compare the original AR step and the smart convergence control. So you can see with the smart convergence control, the AR step card is very simple and concise. So now with both of the original AR step and the smart convergence control, both of them use the 63 increment. And also, we'd like to compare the displacement at this corner marked by arrows. So you can see both of the decks with the original air step and the smart convergence control. So you have to complete the same displacement. So, but the smart convergence control just brings a user very simple selection. And so the second new feature is adaptive time stepping adjustment for transient analysis. So right now, the solution 400 just support a different methodology of adaptive time stepping adjustment. The first one is frequency-based time stepping. Another is the iteration-based time stepping. Also, both are their combination. Here is an example. So this is a 2D beam model as described in Bergen's paper. So this is a 2D beam and subtracted the load at the end. So as you can see in the red figures, the green line shows us the result obtained by the old NL step. With the old NL step card, so review lead to very large time step. So in this case, the nation cannot capture the details of the displacement. So with the new NL step card, we can see the yellow line is completely the same compared with the other solutions. So the new card will give us a very accurate result. And the adapt, there are two keywords for the adaptive time step. So one is adjust, another is M step. So first, if M step is set to -1, so that means you will activate the frequency-based adaptive time step adjustment without bound. So that means without the time step bound. So this method can be combined with the iteration-based adaptive time step adjustment that's controlled by N desire. If the N desire is 0 in the setup, so the time step is only adjusted after the increment converged. So if you don't use the -1, set the M step as between 10 to 200. So that means you will activate the frequency-based adaptive time step, but with bound. So that means it will have some the lower and the up bound for the time step. So in this case, this method cannot be combined with the iteration-based adaptive time step. So that means no matter what you set by N desire, so the value of N desire will be ignored. Here is the first example. That is the cantilevered plate is subject to the rigid sphere at a constant velocity of 20 inches per second. So in this model, we use two different controls. First one is adaptive. We set M step as -1, and the other deck is with the fixed time stepping. So from the right figure, you can see both of these decks will result in the very similar. We can see maybe complete the same result, but with the adaptive time step, it only used the 85 increment. But for the fixed time step model, they use the 400 steps. So compared with the fixed time step, adaptive time step deck will bring in very effective and efficiency the time control. Here's another example that a cantilevered plate is impacted by a deformable cube. So the combination of the frequency-based time step and the iteration-based time step are used in this model. I'm not sure if you can see this movie.
Nope,
Not really.
not visible.
No?
Nope.
Oh, this is terrible. How about this time?
No, not yet.
No.
That's okay. We can.
Okay, sorry.
Make these movies
That's
available,
all.
right?
Yeah, I will stop here. So just from this movie, we can see the deformable cube just dropped and impact the plate, and then the cubic will rebound from the plate and to some height and then jump again. Okay, so let's